Imagine our entire solar system, not just Earth but the Sun, all its planets, moons, asteroids, and comets, embarking on an involuntary voyage. Picture all of it, our cosmic home, zooming directly towards a black hole. It sounds like a plot from a wild science fiction movie, doesn't it? Yet the universe is filled with objects and events that dwarf our everyday experiences. This hypothetical journey pushes the boundaries of what we consider possible. What would such an encounter truly mean for everything we know? This wouldn't be a gentle drift into the unknown. A black hole is often called a cosmic vacuum cleaner, a devourer of light and matter. But it's so much more complex than that simple analogy. It represents a point in space-time where gravity becomes infinitely strong, warping the very fabric of reality. The journey itself, before any dramatic effects, would be unimaginably long. Space is profoundly vast. Even if a black hole were lurking in our galactic neighborhood, the approach would likely span countless millennia. But let's compress time, for the sake of our cosmic exploration. This is where our story of cosmic survival, or transformation, truly begins. Before we dive headfirst into this cosmic encounter, let's pause and ask, what exactly is a black hole? It's not really a hole in the traditional sense, like a hole in the ground. Think of it more as an incredible amount of matter packed into an infinitesimally small space. This super-dense region is called a singularity. The gravity it generates is so overwhelmingly powerful that nothing, not even light, the fastest thing in the universe, can escape its grasp once it crosses a certain boundary. This boundary is known as the event horizon. Black holes come in different sizes, which influences how they interact with their surroundings. Stellar mass black holes are typically a few times the mass of our Sun. They form when a massive star runs out of fuel and its core collapses under its own gravity. Then, there are the supermassive black holes, true giants of the cosmos. These behemoths can be millions or even billions of times the mass of our Sun. Our hypothetical journey could involve either type, each presenting unique horrors. Understanding this fundamental nature of black holes is key to appreciating the sheer scale of the catastrophe that awaits our unsuspecting solar system on its cosmic collision course. Long before any planet gets close enough to be torn apart, the black hole's immense gravity would begin to subtly, then dramatically, perturb the outer reaches of our solar system. The Oort cloud, a vast diffuse sphere of icy bodies believed to surround our solar system far beyond Pluto, would be the first to feel its effects. These loosely bound comets, trillions of them, would be stirred up like dust in a cosmic wind. This disturbance in the Oort cloud would unleash a spectacular, albeit deadly, barrage of comets. Many would be flung out into interstellar space, lost forever, but a significant number would be sent careening inwards, towards the Sun and the planets. Earth and its neighbors would experience an unprecedented increase in comet impacts. Skies once serene would become streaked with these icy visitors, some burning up harmlessly, others posing existential threats. This celestial bombardment would be an early warning sign, a cosmic Morse code signaling the approach of something far more powerful and destructive. The journey, which might have started as a slow drift, would now be picking up pace, transforming into an unstoppable plunge into the gravitational abyss, a cosmic roller coaster with no brakes. The event horizon. This is the defining feature of a black hole, its most famous characteristic. It's not a physical surface you could touch or stand on. Rather, it's an invisible boundary, a point of no return. Once anything, matter, light, or even our entire solar system, crosses this threshold, its fate is sealed. Escape becomes impossible because to escape would require traveling faster than light, which, according to our current understanding of physics, simply cannot happen. As our solar system approaches this critical boundary, strange things would begin to happen to light and perception, at least for any hypothetical outside observer watching us. Light from distant stars would appear bent and distorted around the black hole, a phenomenon known as gravitational lensing. The black hole itself would appear as a perfect sphere of blackness, silhouetted against the backdrop of space. For those within the solar system, the experience of crossing the event horizon of a very large, supermassive black hole might, surprisingly, be initially uneventful. The journey beyond the event horizon is a journey into complete darkness, as no light from the outside universe can penetrate further. Alright, let's dive into Section 5: Gravity's unrelenting grip, the power of tides. One of the most significant effects a black hole exerts on any approaching object, especially, an extended object like a solar system or even a planet, is due to tidal forces. We're all familiar with tides on Earth, right? They're caused by the moon's gravity pulling slightly more strongly on the side of Earth facing it than on the opposite side. This difference in gravitational pull stretches Earth, creating ocean tides. Now imagine that same effect but magnified by orders of magnitude by the black hole's immense gravity. As the solar system gets closer to the black hole, the part of the solar system nearest to the black hole will experience a much stronger gravitational pull than the part farthest away. This differential gravitational force is the essence of tidal forces. The black hole doesn't just pull objects, it tries to stretch them. For our solar system, this means that the planets closer to the black hole would be pulled much more forcefully than those farther away. The very structure of these celestial bodies would be under immense strain, a cosmic tug-of-war they cannot win. Section 6. Stretched to infinity, the fate of spaghettification. Spaghettification. It's a vivid term for what happens when tidal forces become overwhelmingly strong. Imagine an object, say an unlucky planet, falling towards a black hole. As we've discussed, the gravitational pull on the side of the planet, closer to the black hole, is significantly stronger than on the side, farther away. This difference in force doesn't just create tides, it stretches the planet vertically, along the line towards the black hole. Simultaneously, forces around the planet's equator, perpendicular to the fall, would compress it. The planet would be elongated, squeezed, and pulled apart, literally drawn out into a long, thin stream of its constituent matter, like a strand of spaghetti. This process wouldn't be instantaneous, it would be a gradual but relentless dismemberment. First, the planet's atmosphere might be stripped away, then, its crust and mantle would crack and separate. Section 7. Earth's final chapter. A world under siege. Let's focus on our home planet, Earth, as it faces this cosmic cataclysm. Long before spaghettification takes its final toll, life on Earth would become impossible due to a cascade of other devastating effects. As the solar system is dragged closer to the black hole, Earth's orbit around the sun would become highly unstable. The delicate gravitational balance that has maintained our planet's temperate climate for eons would be shattered. Earth might be flung into a much hotter, closer orbit to the sun, or a much colder, distant one, or even ejected from the solar system entirely before the black hole's direct influence becomes dominant. Assuming Earth remains bound and heads towards the black hole along with the sun, the increasing radiation from any accretion disk around the black hole, or from the sun itself being distorted, would scorch the planet's surface. Our atmosphere, our protective blanket, would be stripped away by the intense gravitational forces and radiation. Oceans would boil away into space, leaving behind a barren, cracked wasteland. Section 8. Time's Curious Bend, Relativity in the Extreme. One of the most mind-bending consequences of being near a black hole, as predicted by Einstein's theory of general relativity, is the phenomenon of gravitational time dilation. In very strong gravitational fields, time itself runs slower relative to regions with weaker gravity. So, as our solar system plunges towards the black hole, time for us within the solar system would pass more slowly compared to time for an observer far away watching our descent from a safe distance in a weaker gravitational field. Imagine you had a very powerful telescope and could watch a clock on Earth as it approached the black hole. You would see the seconds on that clock tick by slower and slower. As Earth neared the event horizon, the clock would appear to slow down dramatically, eventually seeming to almost freeze. From your distant perspective, it would look like the solar system takes an infinitely long time to actually cross the event horizon. However, for someone actually on Earth, or within the falling solar system, time would feel perfectly normal. They wouldn't feel any sensation of time slowing down. Section 9. Into the Singularity, the Ultimate Unknown and Our Cosmic Story. Once our solar system, or what's left of it, crosses the event horizon, it is irrevocably on a path to the singularity at the center of the black hole. The singularity is a point of theoretically infinite density, where our current laws of physics break down. We don't truly know what happens at the singularity. General relativity predicts it's a point of zero volume and infinite curvature of spacetime, but most physicists believe that a theory of quantum gravity, which we don't yet have, is needed to describe this ultimate extreme. The journey from the event horizon to the singularity is swift and unstoppable. For a stellar mass black hole, this final plunge might take only microseconds. For a supermassive black hole, it could take minutes or even hours from the perspective of the falling matter. During this fall, the spaghettified remnants of our Sun, Earth, and other planets would be further compressed and heated, eventually losing all individual identity as they merge with the singularity. All the matter and energy that once constituted our solar system would be added to the mass of the black hole.